In this video I want to introduce two important concepts which are related. The first one is the codifferential, also codifferential operator if you want, and the second one is the Dirac operator. The Dirac operator contains the codifferential, so the two are related, and in order to describe the Dirac operator we need the codifferential first. And to introduce the codifferential we first need to remind ourselves of the so-called Hodge dual. So the concept of Hodge dual is important when we discuss differential forms, and since I have already created some videos on differential forms, I will not describe in mathematical detail the Hodge dual in this case, but I will use it. So I will take for granted that you're already familiar with the Hodge dual. I will now refresh some concepts here and there, but I will not write down the mathematical definition of the Hodge dual. Remember that the Hodge dual is defined with a star. So for example we have a p-form omega, so I will assume that omega is a p-form, and I will also define it in mathematical detail in a moment, or in a few minutes if you want. With the forms we are allowed to take the Hodge dual, so this would mean that we take the Hodge dual of omega, and for example let's assume that the p-form is embedded in an n-dimensional space, so let's say lowercase n dimensional, and the p-form can be written in the following manner. For example, omega I1 I2 ... IP, this is a p-form, dx I1 wedge dx I2 wedge ... wedge dx IP. And usually in the definition, I mean, maybe instead of usually I should say sometimes, we have a p factorial in the denominator to account for the fact that there is some counting here when you do the summations, and I have already described such factors in lectures dedicated to differential forms, so allow me to avoid explaining this again in this video, because it is beyond the purpose of this video. I have to assume that we start from some basics, from some background, whatever. And as you can see, this is a p-form. And when we take the Hodge dual transforms the p-form to an n-p form. So for example, if you have a scalar and you take the Hodge dual, the Hodge of the scalar, you get an n form, because a scalar is a zero form if you want, and so on. So if you have a vector which you can think of as a one form, so you can write a one form, and what you get is an n-1 form when you take the Hodge dual. So you can realize this if you think about the mathematical definition of the Hodge dual. I advise you to check it if you are not really familiar with the Hodge dual. You don't need to remember exactly the definition, but this is some kind of schematics that are important in this video. So you have to be familiar with this at least. This is important, because we are going to use it. And in particular, in this case, we have to introduce the codifferential, which is denoted with this delta. So delta omega is defined as plus or minus, so here we have some kind of ambiguity in the signs, and I will discuss the sign. It's not really important, you can either choose a plus or a minus, but I mean, there can be different conventions, and I will choose my own convention, and I will show you later. But this is not the most important part. What's important comes next. So we have the Hodge dual of the exterior derivative. So here we have another important operator in the case of differential forms, which is the exterior derivative. So allow me not to delve into the details of the exterior derivative. I need to assume, I must assume in this video that you are already familiar with the exterior derivative. We are going to use it, so you will I hope that you will remember after I write down the formula for d, this exterior derivative, and because we will use it. Then here, to finish writing down the expression, we have another Hodge dual, so you can see that we apply twice, and then we have the p form omega. So you can take this as a definition. And I will try to describe the importance. I want to emphasize the importance of such an operator, especially when we write down the Dirac operator. I will show you that such an operator is very important. So, a first description of this operator can be given qualitatively in the following case. So, as I said, omega is a p form, right? And if you recall, when we take the Hodge dual of a p form, what we get, so we can write it like this. Let me put the arrow like this. We have something like this, star d, so I will not bother writing down the plus or minus, that's not important in this consideration. And then here I'm going to write n minus p form, because when I take the Hodge of omega from a p form, I move to an n minus p form. And then when I take the exterior derivative, if you remember, I'm going to increase the degree of the form by one unit. So I have something like n minus p plus 1 form. This is what I get qualitatively. And then I'm going to get another Hodge dual again. So when I do that, I have an n minus this number, which is n minus p plus 1 form. And what do I get? I can simplify this n with this n, and I get p minus 1 form. So you can see that when I consider the codifferential, I start from a p form and I decrease by 1 unit the degree. So I go from p to p minus 1. And in a similar manner, if I consider a p form and I take the exterior derivative from a p form with the operator d, I move to a p plus 1. So it's similar, but it's not the same. So in this case, I increase the degree by 1, whereas in this case, I decrease the degree by 1. And now we need to be a little bit more quantitative, not just qualitative, but also quantitative. So if I take the codifferential of a p form, I can consider the p form in the following manner. So I can write it in the following manner: omega I1, I2, dot dot dot, IP, dx I1, wedge, dot dot dot, wedge, dx IP. And we divide by this useful factorial p factorial, like this. So, as I said earlier, as I showed you, we need to create a p minus 1 form starting from a p form of this kind. And since this should be a derivative operator, we need to allow the derivative operator to come into play. So we have a bunch of derivatives that I will represent like this. You can think of this as a covariant derivative to be more general, but let's think of this just as a derivative. And we need to contract this derivative, d alpha, with one of the indices that we have in the form, right? So this is the idea. And if we contract that, for example, we can contract this alpha with the first of these indices. So let's say that we have omega alpha I2 dot 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 IP, and then since we have contracted these two indices, you can see that we have to sum over these p minus 1 indices. So in this case you can see that we have p minus 1 because in here we have p. So we have removed the first one, and here we have p indices. So we have to sum over dx, so over I2, so we have dxi2 wedge dot dot dot, you get the idea, wedge dxip. And of course we need to divide by p factorial, and if you want we need to choose the sign here. If you recall, we can have a plus or a minus, and here I'm going to choose my notation in such a way that I consider a minus like this. Okay, so we set the sign to a minus here. However, if you want, you can consider the contraction with between the derivative and these indices in different manners. So for example, you can contract this index with the second one, and you can do a similar consideration. You can make a similar consideration, and due to the fact that the form is antisymmetric with respect to the indices, so for example this is equal to omega minus omega I2 alpha I3 dot 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 IP. If we swap the order between alpha and I2, we get a minus. So you can easily understand that if you contract this index with the second one, you get something similar, but the overall sign is reversed. So you have a change in the sign, right? But you can still swap the order between these two, alpha and I2, and you flip the sign once more if you think about it. So I hope you get the idea. And in order to keep track of all the terms, since you can always swap the order, what you will get if you contract the index p times, you will get a factor of p here. So you can write this codifferential in this manner. So you can also take this as a definition, as a definition that is actually the same as this one if you do more rigorous mathematics, but in this case I just wanted to give you the intuition without getting lost in all the mathematical details. You can do that. It's not really complicated if you know the definition of the Hodge dual and you just go through the mathematics. You will have to get something like this, apart from the sign, aside from the sign, because this sign can also be a plus if you choose different definitions, but don't be scared by the sign. And if we want, we can divide by p, and we can rewrite this p factorial in the denominator by, so we can rewrite it as p minus 1 factorial. Simple as that. So as I said, the factor p that we wrote here comes from the fact that you can contract the derivative in different manners. So you can have d alpha omega alpha I2 dot dot dot. So allow me not to write all these indices, but I will write IP, and now I'm not considering this minus. And then here you have dxi2 wedge dot 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 wedge dxip. I'm not considering this sign because in this case it's not important. I'm just considering this part. And in principle you can also contract alpha with the second index, and in that case we get a minus. So in that case we get a minus because, I mean, the rule is the following. So the codifferential is, it has alternating signs when we do the summation. So for example, if we consider a p form, we have a minus 1 when we contract with the first index, then we get a plus 1 when we contract with the second index, a minus 1 with the third index, and so on. So we have alternating signs like this. So if you wanted to keep track of this minus, we can put a minus here, and then we can put a plus here. D alpha omega I1 alpha I3 I4 dot 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 IP, and dxi1 wedge dxi3 dot wedge dot 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 wedge dxip. And if we want to be consistent with this notation, since I1 is a dummy index, we can change I1 to I2. It is simply another way of writing it. We have to sum over I2, and the expression is the same as this one if you check, because if we swap the order between alpha and I2, this would become minus d alpha omega alpha I2 I3 dot 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 IP. And therefore you can see that we get a factor of 2 if we put these two together, right? But the idea is the same, so you have to go on and to contract the index with all the p indices that you have here. And at the end of the day, so now let me cancel this because otherwise it's going to get dirty here. What you will get, as I said, is that factor of p that I wrote earlier, and the factor of p simply cancels the p in the p factorial. So we have p divided by p factorial, which is equal to 1 over p minus 1 factorial. And this is what we get in here. But now let me cancel this. So I have shown you how to write the codifferential for a p form. And now what I want to do, I will also cancel these alternating signs here. What I want to do is I want to calculate the exterior derivative of the codifferential of omega. And of course you can use that formula there when you take the exterior derivative. And it's actually quite simple if you remember how to write the exterior derivative. We have, so we still have this minus. Then we have the derivative operator d beta, del beta, which comes from this d. Then I have, I have d alpha from here, del alpha, omega alpha I2, dot 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 IP, divided by p minus 1 factorial, and here you have dx beta, which comes from the fact that we need to contract the beta with the differential, so this is the exterior derivative, and I'm not considering the other factors. I'm just keeping this one, and this is how I define the exterior derivative of the form. I have to take the wedge with the dxi2 wedge dot 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 wedge dxip, like this. So you can see that when we take the exterior derivative of the codifferential, we get back a p form. So this is still a p form because you can see that we have p differentials. And we have written the exterior derivative of the codifferential of the form, but we can also take the codifferential of the exterior derivative of omega. And I want to show you that the two are not the same, because the order in which you write these operators is important. And let's calculate this one, and then, these two will be important in the definition of the Dirac operator, and I want to show you that. So when we take, I have the codifferential of the exterior derivative of omega. The exterior derivative of omega can be written in the following fashion. So we can write it as d beta omega. Here we have I1 dot 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 IP, so we are not contracting beta with these indices because we need to contract it with the differential here. And this is part of the definition of the exterior derivative. Then we have wedge dx I1, wedge dot dot dot, you get the idea, wedge dx IP. Remember that we also have the p factorial here in the definition of the p form. And now we can take the codifferential. You can see here that we have a p plus 1 form. So when we take the codifferential, we will get a p form, so a p plus 1 minus 1. And according to the rules of the codifferential, when we contract the derivative that comes from the codifferential, when we contract it with the first index, we get a minus. So we get minus del beta omega I1 dot 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 IP. And then we need to be a little careful, because when we contract with this beta, of course, this dx beta will not appear, and what will appear is just this set of differentials. So we have dx I1 wedge dot 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 wedge dx IP divided by p factorial. And then we need to contract the derivative with all these indices, one by one. So as you can imagine, we get plus, so when we contract with the second, we get plus d alpha d beta omega alpha I2 dot 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 IP. Then we have dx beta wedge dx I2 wedge dot 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 wedge dx IP. And we divide by p factorial. But remember that we also need to do the same thing contracting the other p minus 1 indices. So at the end of the day, what we will get is a factor p here that we can simplify with this p factorial, so we can write p minus 1 factorial here. And as you can see, this expression is different from the expression that we get here. So when we change the order in which we apply these operators, we get something different. But you can see, for example, that this term is equal to minus this one. They are opposite to each other. So when we sum, so if we, let's say, if we sum these two, d delta plus delta d applied to omega, what we are going to get is, we are going to get just this one. So we are going to get minus d beta, and then we have the p form that we can simply write as omega, just like that. So we get the Laplacian with the sign, but we get a Laplacian of the form which we can write like this. But let me say something more interesting, even more interesting than this actually. So if you recall from differential geometry, if we take the exterior derivative twice of a form, we get 0. And this is actually something quite easy to understand if you think about it, because when you take the exterior derivative twice, you are going to get, now I can do it here, you are going to get some second derivatives of the kind d alpha, let's write it like this, d alpha d beta. Here you have the form omega I1 dot 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 IP, and then we have dx alpha wedge dx beta wedge dx I1 wedge dot 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 wedge dx IP divided by the factorial, but never mind. So you can see that this operator here can also be written as d squared alpha beta if you want, which is equal to d squared beta alpha. So this operator is symmetric, and on the other end here you have something that is anti-symmetric, because this is equal to minus dx beta wedge dx alpha. This means that whatever omega, let's say the second derivative, but in this case the exterior derivative, if you want, or the exterior derivative applied twice must give 0. And if you think about it in a similar fashion, also the codifferential, since it contains the derivative, but let's write it below, also the codifferential applied twice to a form gives 0. Let me say this once more. It's something quite easy to understand, because you are going to get a bunch of derivatives, so two derivatives, d alpha and d beta, which are going to be contracted with the form. So maybe I can write it like this: d alpha d beta omega, and then here you will have alpha beta and a bunch of other indices. But the form is anti-symmetric with respect to alpha and beta, whereas this part is going to be symmetric. This is the idea. So you can understand, even without doing the calculations precisely, you can understand that this is 0 as well. This is 0 and this is 0. And now, if I take the operator d plus delta, so in particular, this expression here is the Dirac operator squared, not the Dirac operator. This is the Dirac operator squared. Dirac operator squared. And you will see why. This is the Dirac operator. It's defined as the Dirac operator. And if we square the Dirac operator, and you always have to think that here we have some form. When we apply this operator, we apply it to a form. So it's as if in here we have a form. But allow me not to write omega. So if you square it, what do you get? You get d squared plus delta squared plus d delta plus delta d. Remember that the order in which you write them is important. So you don't have twice d delta or twice delta d, because they are different. So you have to write them like this. But as I said, when you apply this to omega, let's write it, whatever. When you consider delta squared of omega, you will get 0, so this will give no contribution. And also when you apply d squared to omega, you will get 0. So this will also give 0 contribution. And you will be left with d delta plus delta d applied to omega. So what we did in here is we found the square of the Dirac operator, basically, because we have shown that this is the square of the Dirac operator, so we can write d plus delta squared applied to omega equal to minus, let me write the Laplacian like this, this is the covariant Laplacian if you want, applied to omega. So this sign can also become a plus if you want. If you use different definitions of the codifferential, this could also be a plus. It depends on your definitions. It's not important. But this shows that we have found a way to express the Laplacian. So we found an operator whose square is equal to the Laplacian, basically, minus the Laplacian. And this is important in physics because, for example, in the Dirac equation, we have something similar in quantum field theory. If you square both, let's say, quote-unquote square, the Dirac equation, you will get the Klein-Gordon equation. So the Klein-Gordon equation contains the Laplacian. So if you think about the massless Klein-Gordon equation, you have something like del squared field equal to 0. Whereas if you consider the massless Dirac equation, you have something like gamma mu d mu, where gamma mu, they are the Dirac matrices, applied to some other field, which is a spinor. You can consider this to be a spinor equal to 0. This is the massless equation. But if you square this equation, you can show, this is something that's done in quantum field theory. Now I will not do it in here, but it's quite straightforward. If you know the properties of these Dirac matrices, you get something like d mu psi equal to 0. And you can see that by squaring this object, we get the Laplacian. So in some sense, this is some kind of Dirac operator. And now I will not get into the nuances of this, into the details of this, but let's say that the mathematics is formally equivalent. So we get an operator whose square is the Laplacian. And this operator is important because I will use it in the subsequent part where we continue discussing the article written by Ginestra Bianconi. So gravity derived from entropy, from quantum entropy, and we'll continue next time.